Hi everyone, I'm Samuel and welcome to today's event. So, thank you so much for joining us today. Okay, a few housekeeping items before we get started. So, today's event will be recorded and be made available on our YouTube channel for reference. So, if today is your first time joining us, be sure to join our official page so that you don't miss any updates. In today's event agenda, we will introduce our first project, MalariaX, and you get to know what we aim to accomplish and how we're going to do it. We also have with us today the faculty advisor of the Google Developer Student Clubs at KNUST, and he will be speaking on responsive embedded data acquisition systems for real-life applications, which will be key in how we will use remote sensing to gather data. So today, we officially launch our MalariaX projects. Okay, so let's get into it. So we know that climate change is really pervasive and it's going to have lots of pervasive effects on our lives. But how exactly it's going to affect disease risk is a very big unknown. So when you look at the metabolic rate and all of the development rates and all the biological processes that go on within mosquitoes, you can see that they are really temperature dependent. So there is the strong reason to believe that climate change will have a big effect, but there's a lot of uncertainty in exactly what that effect will look like. So the aim of this project is to predict how climate change will change where and when vector-borne diseases like malaria occur. So together with satellite images, temperature variation, rainfall, and other data sources, we aim to build an algorithm that identifies where mosquito breeding sites likely exist. So in this project, we want to take a mechanistic approach that's breaking down the process of vector transmission into all the component steps and measuring components such as humidity, rainfall, temperature variation, and of course, human activities like vector control and what types of housing people have to help identify breeding sites quicker and more accurately. And of critical importance is the estimation of vector species populations in an area of interest. So traditional approaches in estimating malaria vector populations involve physically collecting vector samples in traps and manually classifying the species. So this is very labor intensive. And so we aim to develop a model that can classify mosquito species and sex from wing beat audio signals, which are suitable to be deployed on small IoT sensor devices. So we are going to need pre-annotated data sets with a Google Maps grade image resolution, weather data, and cloud TPUs, which should be used for training our model. And we are lucky to have with us Dr. Emmanuel Ahene. Dr. Emmanuel Ahene is the co-founder of CyberPass Consults, an international cybersecurity consulting firm that offers IT security services and training for public and private organizations. He is also a lecturer at the Kwame Nkrumah University of Science and Technology with demonstrated research expertise in cybersecurity. And he is our faculty advisor. So, Dr. Ahene, over to you, sir.
Okay, thank you, Sam. I hope everyone can hear me now. First of all, I welcome you all to the Google Developer Students Club meeting here on Zoom. I am Dr. Emmanuel Ahene, as Sam mentioned early on. And today I just want to take you through a few things that you are supposed to know. Okay, so first of all, we would go through what the terms are in terms of our topic for today. Okay, so I'm going to share with you just I think about a single or two pages of slide that may be just necessary as fundamental definitions for what we have to go through today, and then I'll zoom into giving you other details off slides actually that I'm sure that if you would put down notes, it will really help. So first of all, our major topic today is to talk about responsive embedded data acquisition systems. Now, out of that is the term data acquisition. So the first thing that you would quickly want to know is, what is a data acquisition system? And then secondly, you would want to know embedded, what the term embedded actually means. What is an embedded system? And also, once you put them all together, you are able to emphatically determine what the definition for embedded data acquisition systems is. Okay, so let's begin. Data acquisition system is a system that consists of three key elements. All right, so please take note, three key elements. So the first thing is a sensor, and then the second thing is a signal conditioner, and then a converter. Now, this converter is supposed to be an analog to digital converter. So these are three key elements when you talk about a data acquisition system, okay? Now, we know that every system is made up of components. And so if you talk about a data acquisition system, then these are the three components that you would want to actually look out for as far as making it up to be a data acquisition system. So I think most of you have seen what a sensor is. It's actually a small device, a very small device. I can take you to the internet right now and search, so you can all see what a sensor is. I think most of you have heard it before. You might have seen some. And during my undergraduate days, I was privileged to work with sensors in building an automated dust bin. Okay, so where this dust bin, what it does is that it uses an ultrasonic sensor that is able to detect within a space of about 30 centimeters if there is an object approaching. And then when it detects that, we program this such that it opens by itself, and then the user of the bin can throw the trash in it, and then it closes by itself. Okay, so you can actually use a sensor to pick signals from the environment. Okay, so in this particular example I've given, the ultrasonic sensor is actually picking signals of an object, okay, within its environment, and then we programmed it for a space of about 30 centimeters. So within that space, if it detects an object, then it sends over the data, and based on the data is programmed to react in such a way that it enables an opening of the bin and then throwing in of your trash, and then it closes by itself when the object is away. Okay, so that is just a pretty simple example of what you would think of a sensor to do, but I want to show you. So there are different kinds of sensors. Have a look here. We have ultrasonic sensor, and this is the sensor I was privileged to work with during my undergraduate days, as I mentioned. Okay, I would circle it so you know what I'm talking about here. This is an ultrasonic sensor. Okay, and then there is also a gas sensor, right? So, and the color sensor, PR sensor, accelerometer, and so on and so forth. So all of these are sensors. Everything you see here is a sensor, and they are all used for different things at a time. Okay, so with the MalariaX project, basically you would want to identify what kind of sensor would be relevant in building the system. Okay, so you would have to actually consider now each of the sensors have got their limitations and what, or if you like, what they are meant to do. Okay, so that it's not really as a limitation, but it's like what it has been made to do. Okay, so all of these ones. So basically you would also know that by definition, as I have said initially, a sensor is supposed to pick up data from the environment, and when it picks up the data from the environment, it translates it, or if you like, it puts it in the form that is human readable or human understandable. Okay, or if you like, in some cases, machine readable or machine understandable. Okay, that's it. Now, I also want wanted to show you what the second element is, which is the signal conditioner. I will show you a picture of it, but also we have different kinds of signal conditioner. And what it does is that it's just filters the analog signal that is picked up by a sensor. Okay, so you could see that if you are talking about it in terms of component-wise, they are sort of related. So the signal conditioner works on the analog signal that is going to be picked up by the sensor before converting it into digital form, or if you like, a digital information. Okay, so you can also amplify the signal using a signal conditioner, or you can attenuate it, or filter it, calibrate it, and so on and so forth, just so that you would be able to reduce the noise level in it, or if you like, treat it to the point where it's relevant for the project or the work that you're doing. Okay, so there are different types of signal conditioners. If you would Google right now, you will see them in picture. And then the last one is an analog to digital signal converter. Now, this is one of the important elements as far as data acquisition process is concerned. So it's a kind of a chip, and what it does is that it transforms the signal captured from your environment into information that can be explained or understood by processor. Okay, now that means that at this level, you are going to be able to transfer such an information to the computer via some either a data bus or any of the computer connections that should enable you to have data available, readily understandable for processing. Okay, so if we are thinking of our MalariaX project, then these are three key elements that we should be looking at into building our system. Now, I would want to tell you maybe a few reasons why you may have to necessarily look at building a data acquisition system. I think some initially mentioned a few, stating the disadvantage of, or if you like, the labor intensiveness of gathering just from environments. And he was actually mentioning a more easier way, like building up a model that goes on to help in dealing with the data. But also, I would like to add up this, the reason why we may need to look at this MalariaX project in this manner is because we want to improve the efficiency and reliability of the process. Okay, so we are looking at a system that is going to be able to detect maybe some features of environment, and then based on that, run it through a model that has been built to be able to predict the pervasiveness of malaria parasite in a particular environment or a particular region. So this is quite important. So if we want to think of a very efficient and reliable way of developing our MalariaX project, then we need to rather think of building a system that is a DAQ, as in data acquisition system. Now, the reason why we add up embedded here is because, when you talk about embedded systems here, we are also referring to a system that, number one, in some cases is a real-time system, as in it produces the result as in when we need it. Because, if you look at real-time systems, you would have it in three forms. We have a hard real-time system, we have a soft real-time system, and we have a firm real-time system. So with hard real-time systems, you are looking at maybe an embedded system that if there is a failure, or if you like, if there is a delay in its delivery of output, it can cause catastrophe. Okay, so you can think of an example like an airbag, an embedded airbag system in a car. Okay, so the airbag is an embedded system. It's also a real-time system, and it has been programmed in such a way that in case there is a hard collision on the car from the front, it should best open. All right. So, and if it has been programmed to, for example, do this within 3 milliseconds, and then after collision, maybe let's say it's best out in, let's say, 10 milliseconds. Now, it would not be able to save the person in the car, because based on the programming, we are supposed to, or we estimate that within a space of 3 milliseconds, when the airbag bursts out, it's going to be able to save the driver. But if it delays, let's say in 10 milliseconds, it works all right, but eventually there's catastrophe because the driver is going to die, okay, because of the failure, or if you like, the delay of such a system. So this is classified as a hard real-time embedded system, okay. Now, a soft real-time system, or if you like, an embedded system, that one, delays are not really a big deal, actually. There could be delay in delivery, but people only attribute it to, let's say, the how poor the system has been programmed, or how the program or how the software is really not so good. Okay, so maybe you can think of an example of a real-time system, like, say, let's say, a software that allows you to print, from your printer. Okay, so let's say you give a print command, and it's supposed to print, but it delays a bit. Maybe you were expecting it quite fast, but it delays and prints out, let's say, in the next 5 minutes. Okay, it doesn't kill, it doesn't cause any catastrophe, but eventually you attribute it to the fact that, oh, maybe the printer is too bad, or the software has not been programmed so well. So a failure in delivery in such a system, or an embedded system, doesn't actually cause catastrophe, but it will only let us know how bad the system is. Okay. All right. Another thing to look at is the firm one. The firm one, you can think of something like maybe a robotic weed killer. Okay, is an example, a robotic weed killer, or maybe like our MalariaX project. Okay, so if you think of a robotic weed killer, that one is supposed to be actually checking when it goes to, say, for example, you give the robot a land space, and then there is so much weed on it, it's competing with the plants, and you just program the robot to spray only on the weeds, not the plant. Okay, so this is a kind of system where if the robot fails in delivering its objective by spraying, for example, on the plant, what happens is that it is going to get the plant destroyed, right? So, and in the firm real-time embedded system, for example, in this robotic weed killer, we are expecting that the system would work fine, as in being spraying on the weed only without spraying on the plant. But maybe just a mistake, or maybe 2 mistakes by the robot, wouldn't be considered as catastrophe. But if the robot continues to make a mistake in spraying on the plant, then it will deteriorate the system. Okay, it leads to catastrophe. So that is a firm real-time system, or real-time embedded system. So you build an embedded robot, embedded system, or like the robotic weed sprayer, and if you classify in the firm real-time system, then this particular system, just the failure is okay, 2 failures are okay. But if the failure continues to happen, then it will bring catastrophe, because eventually it will not be able to deliver its expected output. It will eventually spray everything, the plants and including the weed. Okay, so now when we are building our systems, we need to think of it in this way. So we have to think of building the MalariaX project. Maybe we can classify it in the area of a firm real-time embedded system, because maybe its continuous failure may lead to something deteriorating, because we have an objective in this, just to ensure that we are going to be able to build a system that will enable us to overcome the challenges as far as malaria is concerned. Okay, so now I'm saying all these things just to broaden your scope of understanding. If you're building an embedded data acquisition system, then think of it in the firm zone, you're going to program it in such a way that the system is able to reorganize itself in terms of one or two failure, and then get back on track, learn from the failure, and then get back on track. So that is one of the things I want to actually put before you today. Okay, so you can still keep on searching, and let's get more facts around as far as the MalariaX project is concerned. But basically, if we are building this system, we should be looking out to, first of all, classify it in the firm zone. And then also the second thing is to also ensure that all these three key elements are in there. We have a sensor in there. We determine the kind of sensor we want, we program it, and then get it to be picking up environmental data. And then we would get a signal conditional and then a converter as well. Okay, just to assure that we have the objectives of the project being met.